that was a very fast, stuff about DFT in general, right? So this one now is more of an intro to machine learning. How many people have done some machine learning? Raise your hand. Okay, much fewer, right? So how many people here are sort of graduate students? Raise your hand if you're a graduate student. Right, so lots of you, right? So I'm telling you now, while you're in graduate school, do some machine learning. And later, you'll come and thank me that I told you to do that. And I will want 10% of your extra earnings that you make because you did some machine learning in graduate school. Okay. It is, obviously huge. And now we're learning it's a little dangerous, right? I don't know if you've been following the news. So actually, if you thought I had too much material in that lecture, wait, you see this one. So I'm going to try to very quickly give you a flavor of machine learning things. I'm not going to talk about electronic structure, just machine learning, right? So one of the reasons I can do this is I now teach a machine learning class at UC Irvine. It's graduate level. It's in fact mostly advanced graduate students. There's usually about 30 a year. Half chemistry, a quarter physics, and a quarter materials. Most of the people are experimental people, not computational people. Most of the work in the course is there's like 10 Jupyter notebooks that the students run for homework, and it's almost always the same every year. The students say the worst part of the course is having to run those stupid Jupyter notebooks because they have to run them like hours and hours and hours. And they also say the best part of the course is the Jupyter notebooks because that's where you learn, right? You learn by doing it, right? And the students don't need to code themselves. I've designed the course with a couple of my students so that you don't need to be able to code because there are experimental chemists doing atmospheric chemistry or something like this. They have no background in this kind of stuff. And then many of the students go on to use machine learning in their research. A big fraction are materials, but then others are sort of bio type stuff. Okay. This was from a few years ago, some blog posts, but this is, and this isn't just an exponential, right? It's an exponential with a crazy constant of 26,000 publications kind of thing. But this is from 5 or 6 years ago, right? This number has gone through the roof. The topics that I cover are these kinds of topics, and we'll move very quickly through some of them. Also, and we'll do that in these, in tomorrow's lectures. The third one will be about sort of machine learning in science, right? How it interacts with science. But this is just machine learning generally. So it's a collection of algorithms, right? And given a task and some measure of performance, the performance improves with experience, meaning more data. More data, it should be better. It's used for many artificial intelligence applications, and it's not much related to human intelligence, right? It's very hard for us to understand why it works. So now, the planet is full of vast, cheap computing resources, and full of electronic data, right? Collected all over the place with all sorts of things. And well, we think we can afford, incredibly wasteful algorithms. They are incredibly wasteful, and they are generating lots of CO2. Big tech companies don't tell you about that. There were previous epochs in which machine learning looked like it was going to take off, and then it didn't. But this one started about 15 years ago or so, and as I say, it just keeps growing and growing, right? So first was, the Karpov got beaten by Deep Blue, I think. But then the real machine learning starts with Go, right? Because you cannot evaluate all the possibilities, no chance. And wasn't it Korean who was the Go maths? Sorry, guys. Google Translate. I used to do this great thing where, when I referee one of your papers, right? And I don't want you to know I'm the referee, right? So what I would do is I go to Google Translate and I hit Chinese. I take my referee report and turn it into Chinese. Then open another browser, take that thing and translate it back to English, right? And there'd be all these mistakes. And then I send in my referee report and no one would think it was me, right? Except on a certain day, I think it was 2018, I do this and it comes back almost perfect English, except it's corrected a few of my phrases, right? Like that. And what had happened was Google hired lots of these top computer science people to work on that problem. They thought it would take 10 years to make a better translator. It took them about a year, and another 6 months. And then one day they turn it on, and like that, you can start translating this language to that language, and it's almost perfect. Image processing, obviously. Self-driving cars, voice recognition. I guess this must be Deep Blue. And this is this famous MNIST set of 80,000 postal codes. People write out the postal codes, at least they used to in the US. And recognize your handwriting. This is one of the standard data sets where algorithms show neural networks basically show what they can do. Okay, so this is summary of the aims of my machine learning course. And one of the reasons is this is what I did in the fall when I was teaching the course. But of course, this was written by ChatGPT. I just gave it the syllabus, and this is what I haven't changed anything. This is what it produced, right? And it explains what my course is about, what the aims are. I just gave it the syllabus. So you may have seen that, what's his name? Gregory Hinton just resigned from Google, who was one of the people who, one of the founders of this field. He had to resign from Google so he could say out loud that he thought all these large language models are really dangerous. Well, I get very worried about this. Okay, so the essential idea of machine learning: you have a data set, you choose an algorithm, and it has some model inside it, often with parameters. You train to choose the best model, and you test on some holdout set of your data. We'll get to that, and then you predict on new data. That's what machine learning is. So there's a few different types of problems. Supervised learning is when you have data where you sort of know what the answer is for that data, and you want to do new data. And there's two types. Regression is fitting functions, continuous functions of continuous variables. Classification is when the output is, say, binary or it's in bins. Yes or no, is this a picture of a kitten? And then there's unsupervised, where you don't have these labels. But is there a pattern in the data? And then there's reinforcement learning, which I'm not going to talk about because there isn't time. So these are the kinds of tasks. Now, it turns out that in a certain sense, all these tasks are very closely related. You can use one to do the others. So fitting a straight line. So if you're in science, stuff again. Okay. Yes, that works. So I start the course with the simulated data and of the ideal gas law. How many people have heard of the ideal gas law? Raise your hand. Good. Right. So PV equals NKT, right? So this is pressure versus temperature. So this should be a straight line, and it turns out there was a guy called Gay-Lussac who first noticed this in, I guess, the 18th century. And so we have simulated data, and you have to fit it with a straight line. And we talk about how you do that. And one of the nice things you can do is if you have such data, this is temperature in Celsius, so room temperature up to boiling water, you can actually extrapolate and try to figure out what the absolute zero of temperature is. But that turns out to be like too simple a case. A nice example is just fitting a function in one dimension. And suppose you have noisy data, right? And so what's different, sort of, we're going to see about machine learning and why it has taken getting very powerful computers to do it the way we now do it, is because we're going to think about not just the sort of noise in the data, but also the uncertainty in the model that we're going to use to fit the data. And accounting for that uncertainty is far more expensive than just the uncertainty in the data. But this is what I want to show you is a standard thing. So here we have some noisy data, and then we're going to see that we have methods for fitting it. And using this particular method, which I'll get back to, kernel ridge regression, we can sort of set it so that it can only produce very smooth curves. And this is a big underfit, where the curve is too smooth and we can see there's really something going on. Then if we set this thing called the noise level to much lower, you see something that looks like a reasonable fit to the curve. And then if you set it to be very, very small, you see that you fit all the data, or almost all the data, almost perfectly. But what you're doing is you're fitting the noise in the data. You're making it go through every point. And this is not good either, right? So one of the key things is finding when a fit is good and when you haven't overfit the specific data that you have. So this is the simplest case. It's continuous variables fitting a function. And there are all sorts of things that you could be fitting, and they don't need to be just one-dimensional. So this is fitting functions on steroids. So the variable x is replaced by a vector, and it may have thousands of entries, right? So those MNIST digit things, they have, I think, 780 pixels in one of those figures. So then it's 780, it's a dimensional vector. The output might also be a vector, and you have to find a good approximation of this function. And now these days, you may have over 100 million data points as well. So that's another issue. And you can always take a regression algorithm that's fitting a function, and you can turn it into a classifier, and let's say it's binary classification. So you make a fitting function, and if that function is greater than a half, you say that the thing is 1, and if it's less than a half, that it's 0. You just make up some rule, and then you try to find the F that gives you the best classification algorithm. So, you know, you have a bunch of data and the data is labeled either black or white, or we're going to see blue or orange. Okay, and now here are references, and actually this is kind of interesting. These are a bunch of books that I read when I was putting together the course. They're all different, they all emphasize different aspects of machine learning. And the interesting thing is, so you can go online, right, and you can get lots of material, endless books, even pretty good video course material, free, teaching you about machine learning. The reason the students come to my class is because there's too much. You don't know, and you don't want to learn about machine learning in general. You want to learn about the bits that are useful for using it for scientific problems, for your kind of problems. So this one here, deep learning book, I discovered this is what all the folks at Google use as a basic operating manual. Is this good fellow running video book. This one here is also a really nice book by Bishop. He's at Microsoft. And this is more like a traditional textbook. And then actually these ones here are very nice. It's something called the theory of statistical learning, and it's sort of basic statistics principles behind machine learning. Okay, so that's just the general thing. The bias variance trade-off. So in every estimate, there's both bias and variance. And in fact, that's what you're seeing when you look between overfitting and underfitting. Bias is the error on the training data, and the variance is the additional error on the test data. We'll see that in a minute. So you can always fit your training data better, which reduces the bias, but often it'll be worse on the test data. And you can make more complex models that fit your data better, but then they'll generalize worse. And this is a standard picture, I think, from Wikipedia or something. Right, so these are low bias situations where your average is close to the bullseye. Here, your average is off. But this is high variance, where the spread around the average is big. And this is high variance and high bias. And the trouble is figuring out what to do. You always divide up your data, right? Whatever data you have, you always take out some fraction, preferably chosen at random. Often about 20% of the data. And you train on the rest of the data to choose the parameters, and then you're going to test it on the stuff you left out. So you're not allowed to train your parameters on the test data. As if you do, you corrupt the statistics, that you build bias into your method by accident. And when I first started learning about this, I learned it from one of the sort of gurus in the field, and got yelled at quite a few times for because we would make these mistakes. And it's funny, I tell the students this over and over again: do not do this. And then later, I'm often on one of their advancement to candidacy exams or whatever you have here, and they're doing it. Because, especially if often it's an experimental situation, right? And you just don't have enough data, right? And so then the human thing is to train on all of it. Okay, so here we have, if you have a model that is not complex enough, as in it'll have some inherent bias. So this is the in-sample error. This is the out-of-sample error. So as you increase the number of training points, these two will come together. So this is the bias built into your model, and this is the variance. And if you have enough data, then those two will come together. But usually you don't. And this is if you can increase, for a fixed amount of data, if you can increase the model complexity. And what will happen is as you increase the complexity, the bias goes down, and the variance goes up. So the total error will actually have a minimum somewhere in between. So this problem is called regularization. How do you pick this point, this magic point where you're minimizing the error in your out-of-sample data, your test data? So it'll turn out it penalizes large weights. We'll see that in your fit. And it's usually controlled by some sort of hyperparameter, not the ones you find by optimizing, but you sort of determine it some other way. And the more you regularize, the smoother the curve becomes, and the less you regularize, you fit the data. So you often peel off this 20%, and then also we'll do cross-validation, where you take different 20%. So I'll show you that in a minute. Okay, so one of the older models is something called kernel bridge regression, where you fit a function with a linear combination of these kernels this kernel evaluated on your data. So you want to fit this function f of x, and you do it with a sum of kernels, each evaluated on one data point, and the kernel measures the distance between the point you're probing and the data point that you have. Very often people use Gaussian kernels because they have some very nice properties. But you have to decide what the length scale of the Gaussian is, and that's one of your hyperparameters. And then the second one is this noise level here, which is what was being adjusted in those figures. So you have to choose them yourself. And in the simple case of kernel bridge regression, it's unusual because, so this is called the cost function. So this is measuring the error in your fit, but then this is the regularizer, which is the thing you can adjust in order to make it not overfit. But in this case, because the cost function is so simple, you can actually do linear algebra and figure out the formula for what these weights should be. You can calculate them. For example, this K here is the matrix of Kij, where you put in Xi and Xj. So usually these days it's too complicated to do that by linear algebra. So you have to find some descent method to minimize your cost function. Everybody following? Okay. You have this parametric model, you have these weights that you optimize on the training data, you have the hyperparameters, and you have this loss function. Regularizer gives you a penalty for large alpha, the analytic solution. Okay, so this is, then what you do is you throw away 20%, that's going to be for testing. Actually, this language is not quite right. And then also we often take out different 20% to do cross-validation, but we've already taken out 20% for testing data. And then we pick so by doing this validation, it's like you're doing a mini test data, and then you might take the median of these values as being your bet fit for the hyperparameters. And in this one here, where we set the noise level to 0.5, when you do the cross-validation, it comes out to be 0.46, and this is the fit that comes out. So by doing this kind of procedure, you're regularizing, which is balancing the complexity of the model with the noise in your data, and something sensible comes out, and in many cases, it gives you the best that you can do with the data that you have, more or less. Okay. You can, here we're looking at least squares, right? So we measure our error, it seems very natural as root mean square error. We've learned that somewhere long ago in high school, I think, or something like this, right? But actually you can use all sorts of other norms. Take any power. So the L2 norm is the standard least squares. People often use this L1 norm called Manhattan, which is just the absolute values, and it has some computational advantages. Now, if you have many features, so if P is so the features are the dimensions of your input, and if you want to make a linear model of your inputs, sadly, formatting. Okay, gradient descent is a big thing. So in the case of the kernel ridge regression, we can use linear algebra to get our alphas, our weights. For neural networks and things like that, no chance. There are no simple formulas. So you have your cost function, and it's a function of gazillion variables, and you have to minimize it, right? You have to find a minimum, or at least a minimum. In fact, in general, there are many minima. And you know, we know lots of math things you can prove if things are convex, but most of these problems are not convex. So people use a technique called stochastic gradient descent. We'll see what that is. And you take points at random to take steps. And of course, you have to decide how big your step should be. If you take too big steps, you actually start going back up the well. But then if you take too small steps, you have to use lots and lots of computer power to get to the bottom, right? Each step doesn't get you very far. And yes, so things can be convex, and if they're convex, it's great because you're guaranteed a single unique minimum of a convex function, and in virtually no machine learning problem that you'd use today could you prove that it's convex, right? So in fact, the whole field is full of mathematical proofs that are totally irrelevant to the practical application of machine learning, because once you get to neural networks, they're so nonlinear that no one can prove anything about them. The math people actually are sort of catching up a bit, but generally speaking, so in computer science, there are people who study the math of machine learning, but they sort of prove theorems about idealized conditions that are largely or even totally irrelevant to practical algorithm. And basically you can see that is, you could ask, given a certain problem, given a certain data set, will a given machine learning algorithm work? You should be able to characterize what are the problems that the algorithm will work for. And for virtually none of the popular algorithms can improve. Oh yeah, so this was from one of my students in the class. So this is computer science, this is statistics, mathematics, and this is machine learning, right? Okay. So range regression is minimizing the least square error with a regularizer. So this kernel trick is a way of going from things that are linear in X to much more complicated in X. This is what I just said. Okay, Bayesian thinking. How many people here have heard of Bayesian stuff? A little bit, right? So statistics, it turns out, is more subtle than you realize when you learn it in the textbooks. We usually, as sort of physical scientists, you learn a little statistics, right? We don't actually learn real statistics. So Bayes was this guy who writes down this very simple formula, which we'll get to. But as physical scientists, right, we usually think this way. So we're taught this idea, they talk about at least a lot in the US, hypothesis-driven science. And it means you have a hypothesis about what's going on, you run the experiment, and you see if the data confirms your hypothesis or invalidates it. So that's the likelihood is, given a certain model of how things are going, what is the probability that you get the data that you got? And this is, so if you know how to do probability things, you can work this out, right? Usually you have a formula and it will calculate that. So, you have a jar of black balls and white balls, and then the probability of picking out a white ball is the fraction that are white, right? So the model is then how many black and how many white balls are in the jar. Now, in Bayesian thinking, you also have to put in the probability that the model is correct without any reference to any data. And that, as scientists, that's kind of a little uncomfortable, right? How would you know whether a model is correct? But we'll see that it turns out to have advantages. And then they talk about the posterior, so that's the prior, and the posterior is the probability of the model given the data. So given the data that you measured, how likely was a given model to produce that? I know how likely is it that that model is correct. And so what Bayes says is just this very simple statement, right, of conditional probabilities. The probability of the model given the data is equal to the probability of the data given the model times the ratio of these two probabilities. And what you can do is, if you have a probability for models, you can use it to, and then you can calculate this guy, you can then figure out the probability of the model given the data, which we'll see is often more accurate than you would do just calculating the maximum likelihood. But it requires these prior probabilities. So in a classical or frequentist approach, you tend to suppose you have a model with a single set of parameters. So you have some theory about what is going on, and there are definite parameters in the model. Given those, whatever they are, right, you calculate the probabilities of the data, and you use that to then estimate the value of those parameters. Now, what's a bit naive about that, but it is the way we think as scientists, is that there is a single model producing your data. Because we're always thinking, right, there are laws about these things. There's Schrodinger's equation, there's Newton's equations. There is some sort of deterministic set of things that's happening, right? Whereas instead, of course, you can account for the uncertainty in the model, right? So you admit that there's a range of possible models that could be generating your data. And again, this is the same statement. Data is the variables in the model. So the posterior is likelihood times the prior. So what actually happens is when you apply these Bayesian ideas, you can often come up with if you have a limited amount of data and a lot of computational power, you can come up with better estimates given that you don't have enough data. So all the classical thinking, if you have infinite amounts of data, that's all fine. You'll get to the same answer if you do this Bayesian thing. And the Bayesian thing is more computationally expensive because you include uncertainties in the model. And actually, you know, if you think about these models are sort of functions in huge spaces, and so searching that space and accounting for the uncertainty in the model is actually usually much more computationally expensive than just the uncertainty in the data. So, but one of the weird things is you must give the prior distribution. Your answers depend on the prior distribution. It makes no difference if the amount of data goes to infinity. Okay. And also you can keep updating Bayes. Once you get more data, you can use it to refine your estimates. We're not going to go through this in detail, but what this derivation ends up showing is, yes, if you analyze linear regression, like we have been doing, and you do a Bayesian analysis, and you choose the prior distribution to be a Gaussian with a certain width. So that's your distribution of models before you start. Then you find the posterior is a Gaussian, and with mean equal to the weights given by the frequentist linear regression with that noise level. So what happens is when you feed in the Gaussian prior distribution and you say that your error is the least squares function, it will pop out that the width of the Gaussian is the noise level that we were just talking about. So what it's saying is that if you analyze just doing the least squares thing in a Bayesian setting, with a Gaussian distribution, and by the way, it's always good in Bayes to have some spread, because you want to have at least some prior probability of even the most unlikely events in case they turn out to be what the data is telling you. As long as it's not zero, if it's zero, then you could never get a finite probability no matter what the data tells you. Yeah. Oh, yeah. So here we go. So if you do an estimate based on the maximum a priori posterior estimate with the Gaussian prior, you get exactly the algorithm for turning on this lambda, this noise level, which works as a regularizer. So Bayesian prior probability distributions regularize your machine learning procedure. So this is a way of thinking about why you have this regularization. Underlying all the machine learning algorithms is the joint probability of your data and the model. if you knew that joint probability, you can calculate everything that you could possibly want. However, it's like brutally expensive to estimate this object. And once you have it, it's called a generative model because you could actually use it to generate synthetic data. And if you have that, you can calculate sort of everything that you might want. So it's easy then to extract everything that you need. And in a sense, so this is called density estimation. You know, all machine learning, in a sense, is a version of density estimation. But in reality, you often only want to know what is the probability of the model given the data. That's called discriminative. And then, but in actual fact, you often just calculate the discriminant function. So when we do that kernel ridge regression, we're just sort of estimating f of x without worrying about any of the probabilities. And this is the cheapest thing to do, and that's what most machine learning methods do. But then you can't pull out other interesting information. Okay, last topic is neural networks. So these were proposed long ago. They're roughly designed to mimic a human brain. The first one was called a perceptron from I think the 50s. That's why the basic unit is called a neuron. Crucial aspects are that these little guys are nonlinear, and that the nonlinearity is amplified by many layers. And many of the, virtually everything we see today is using deep neural networks. Deep just means that you have at least 2 layers. So what happens is you just set up these networks to take in a certain bunch of inputs with a certain bunch of weights, and that you just calculate this guy coming out. But instead of just taking this guy, you feed him into some nonlinear function. And that nonlinearity plays a huge role. So it's called the activation function. And these are your input. This is your input layer. This is an output layer. And then in between, there are these hidden layers. And this is what they call a fully connected network, where every node in a given layer is connected to every other node. There are lots of different arrangements of how the nodes are connected for very specific purposes. And you can prove that you can't make an either-or gate unless your activation function is nonlinear in some way. So they're called artificial neural networks, and this is a sort of general version, also called feed-forward. And there are other kinds that people use for specific purposes. So these little functions are, these days they absolutely need to be differentiable, because it turns out in the last couple of years, people have figured out that you want to be able to differentiate everything with respect to the inputs analytically. And this is not that hard. It's really just a chain rule applied to your whole neural network. And there's a thing called the backpropagation algorithm that does this. And now most codes have this built in from the start. And then you also want to avoid saturating. You don't want your little function to become either too negative or too positive, because then the derivative will vanish. And if the derivative inside one of these guys goes to 0, it means that the gradient of your cost function will be very insensitive to that. which means that as you sort of go around trying to minimize this thing, if you have to move this guy, it will take many, many steps because it won't recognize it as being important. Okay, we're going to have to finish quickly. So stochastic gradient descent is one of the basic ways of minimizing the cost function in neural network. And that. So yeah, they learn features, so you don't have to sort of massage the data very often. And nowadays, people will have 100 billion data points. And what's happening is, as you go to crazy amounts of data, if you have a bigger and bigger neural network, it will keep improving its performance. So if you take things like kernel ridge regression, it will flatten out no matter how much data you have. If you keep growing the size of the neural network, you can get better and better performance. And ultimately, this is what's going on inside these large language models, where it takes Facebook or something to develop one of these, because there's so much data and the neural network is so. What I end the course on is looking at the synthetic data for Boyle's law. So that's another of those gas laws, and it says that the pressure for a fixed temperature is inversely proportional to the volume. And then we try to fit the pressure versus the volume curve with polynomials of positive powers. So this is the noisy data, and this is the polynomial fit of degree 8. And you can see that it fits very well, the data, and it's not overfit. We do our regularization inside the region where you have the training data. But of course, the polynomial fitting, as soon as you extrapolate, it gives you a terrible answer, right? So outside the region of training data, it can be totally wrong. But there's a thing called Boyle's law, which is that the pressure in this case is inversely proportional to the volume. So yeah, we can sort of fit it as well as we like. And you'll never find that the pressure times the volume equals a constant, because you haven't put in v to the minus 1 as one of the possible inputs. If you put that in, you'll get a perfect fit, but without it, and you won't ever find it, right? It can't give you, it can only do this fitting, right? It cannot tell you sort of how you should fit. Here's putting in v to the minus 1, and you see it's just perfect. Pressure proportional to inverse volume. So you could feed all this, this data to a neural network, and it will never find pressure is proportional to inverse volume, right? It will keep going up to higher and higher powers, making it more and more complex, asking for more and more data, and it will give you a better and better fit, but only in that range, and this will not produce this. Now, people are working on something called symbolic regression, which will get you past that, but it's actually a very hard thing. Okay, so machine learning is just a collection of tools for analyzing fitting, very complex data. Simple cases and algorithms do have derivations and proofs of how they should work. But most applications are highly nonlinear with no guarantees. You have to try things out. And neural networks have come to dominate because performance can keep improving with data. And but they need lots and lots of data, much more than the old-fashioned methods. And again, you don't need to do feature engineering but only if you can afford your electricity bill. Right? Okay, I think that's it. Yeah.